Il faut que tu partages.
Ah oui, oui, oui. Ma chère stream.
Alors, je sais pas si tu partages tous les camps de la présentation.
Normalement, que le desktop de là.
Oui, mais donc tous les camps.
Oui.
Oui, comme ça, ils voient ça et ils rentrent dans le groupe aussi.
Ouais, après, c'est qu'en dessous, j'ai la présentation.
Bien. Voilà, je peux vous attendre de mon côté aussi, hein, l'écran, il sert à rien. Vous avez compris pour Toulouse. Avant de commencer, je vais vous dire quelques mots. Donc, je parle aussi aux gens qui sont en ligne. On aura deux pour l'instant. Je ne sais pas si vous attendez plus de monde. Vous avez dit 8. Mais il y en a qui le voient par enregistrement.
Oui, qui sont trop en décalage.
S'ils sont à la côte ouest. Ouais. OK. Donc, je suis le frère Hélène, c'est moi qui suis responsable du cours, mais je n'enseigne pas dedans. Donc, si vous voulez me parler, c'est maintenant. Mais sinon, mon bureau est là-bas pour ceux qui sont au local, pour ceux qui sont à distance. Donc, je vais prendre 5 minutes au début pour voir si vous avez des questions sur l'organisation, sur le déroulement, soit des cours, soit de l'évaluation. Normalement, vous avez toutes les infos sur le site web. Je ne sais pas si vous avez eu le lien. C'est pas pratique. Je voudrais quand même dû vous le donner. Tu peux zoomer sur le lien pour que tout le monde l'ait. Euh, bon,
Je pense que c'est plus inversé.
un peu plus.
Et là, ça zoome juste la page.
Ah ouais, pas de chance. C'est rufinv.github.io/intro to AI avec un majuscule A, I, intro et AI en majuscule, tiret classe, CLAS, S. Ça marche? Vous n'êtes pas connecté? Vous avez du ROM normalement ici. Hein. Et du ROM.
Tu sais, les joueurs,
Ouais. Parce que, non, mais c'est important que vous soyez connectés pour les notebooks. Parce que les notebooks, vous allez donc les TP, la partie pratique du cours, vous allez la faire sur des notebooks, sur Google Colab, donc à distance. Donc, si vous n'avez pas de connexion Internet, on va être embêté. Normalement, vous devez avoir et du ROM parce que vous êtes étudiant. Et du coup, vous devez avoir moyen de vous connecter au Wi-Fi ici.
non, c'est bon.
Ouais. OK. Si vous ne l'avez pas, essayez d'avoir pour la prochaine fois. Il faut récupérer des identifiants, etc. Parce que sans Internet, vous allez être un peu embêté. OK. Ensuite, donc, sur cette page-là, vous avez le planning du cours, en tout cas les parties qu'on connaît déjà, parce qu'il y a deux cours à la fin, Mathieu Serrurier qui est marqué ici et Paul Monsara qui n'est pas marqué ici. Comme c'est pas nous qui l'avons organisé, on ne sait pas où c'est, on ne sait pas quand c'est, mais c'est après. Donc là, vous avez au moins le planning jusqu'à la fin du mois. C'est tous les vendredis et tous les lundis dans cette salle de 14h à 16h et en visio. Notamment, donc c'est un peu dommage de ne pas l'avoir eu à l'avance, je pensais qu'on vous l'avait communiqué. Vous avez sous le planning des informations sur les prérequis en termes de connaissances de programmation, de Python, avec des liens pour vous mettre à jour si ça vous manquait. Là, ça va être un peu juste pour vous mettre à jour avant aujourd'hui, mais n'hésitez pas à aller les voir après. Normalement, essayez d'adapter le cours à votre niveau, mais si c'est pas le cas, ben, essayez d'adapter votre niveau au cours. Et enfin, vous avez les informations en bas là sur l'évaluation. La proposition qu'on avait faite, c'était de faire une évaluation sur projet individuel. Et donc, tout était expliqué là. Je ne vais pas revenir dessus. Je voulais juste répondre à vos questions éventuelles si vous en aviez. Mais là, on n'a pas le temps. Donc, je vous invite à lire ça. Le principe, c'est que ça sera des projets individuels qui doivent être rendus, c'est marqué, avant le 1er mai. Voilà, sachant que le cours finit fin mars, début avril. Ça vous laisse un peu le temps de faire votre projet. Le but, c'est pas d'y passer un mois. Hein, c'est un travail personnel, mais bon, faut y passer quelques heures. Et c'est indiqué ici ce qu'on attend de vous. Et c'est vous qui choisirez sur quel aspect du cours vous souhaitez travailler. Et il n'y en a pas un qui est meilleur que l'autre ou qui donne des meilleures notes que l'autre. Donc, si je ne réponds pas à ces questions-là, est-ce que vous aviez des questions, à part ça, sur l'organisation du cours, sur le planning, sur les modalités pratiques? Non? S'il y a des questions, n'hésitez pas à m'envoyer un email. Je crois que le lien est en bas de la page. Peut-être. Je sais pas. Non. Vous trouverez.
De toute façon, il y a
Ah, voilà. Il est là. Et voilà. Donc, aujourd'hui, je vous laisse pour la première partie, introduction au réseau de neurones, avec Leopold, qui est étudiant en thèse au CERCO ici, et dans Maytie. Et je crois que le cours doit être en anglais. Ouais. So we switch to English.
Yes.
And good luck.
Here we go. Bon, déjà, le cours va être en anglais, mais si jamais vous avez des questions, parce que parfois il y a des aspects techniques, donc s'il y a des questions que vous voulez poser en français, parce que vous êtes, enfin, il y a des termes que vous n'avez pas en anglais, il ne faut pas hésiter. Hein. C'est juste le talk qui est donné en anglais. À côté, on peut parler en français sans souci, même pendant les TP. Voilà. Il y aura un petit peu de maths, pas trop. Donc, je connais pas, aucun doctorant sait si vous êtes à l'aise avec les maths, la programmation ou pas. Pas du tout. Alors, en programmation, vous connaissez Python? Vous avez déjà... D'accord. Parce qu'on nous a dit que vous aviez des bonnes bases en Python. Ok. Donc, du coup, les TP pourront peut-être être un peu compliqués. On passera ensemble dessus, du coup. Et au niveau maths, calcul de matrice, dérivation, ça va. Ok, bon, de toute façon, il y a des petits rappels. On passera ça. Si vous ne comprenez pas, c'est pas la partie la plus importante du cours, c'est les détails techniques. Voilà. Donc, now switch to English because the lessons have to be in English. So this first part will be about neural network history and foundation. So it's given by me, Leopold Maytie. And it's just an short, not short, but an introduction about generality about neural networks. And so this is a bit the content of all the course, not especially this one, but all these lessons that you will have during this month. So we'll begin with a neural network, and we will see after some computer vision problem with Benjamin de Villers, for example. Then we will pass to NLP. So NLP is for language, natural language processing, with 2 or 3 different people. And at the end, we will switch to audio problem. So how to treat audio through a neural network. These are some examples that you will see during each lessons. And today it will just be an introduction about what is a neural network, what is deep learning, how to make a neural network, etc., how to solve problems with deep learning. So just let's begin to define a bit different sets. So there is this large artificial intelligence field, which englobe a lot of different things, like machine learning is a subset here, but also robotic, logic, etc. And inside this artificial intelligence field, there is a subset called machine learning, where we focus to make algorithms that learn how to solve a task without explicitly programming them to solve it. And here we will focus even more on a smaller field called deep learning, which is a subset of machine learning where you have neural networks that are deep, so with multiple layers. So here is a more detailed presentation of artificial intelligence. You have on the top some symbolic artificial intelligence, so good old-fashioned AI with expert system. You will not see this during this lesson. For this, you just give some expert knowledge to your algorithm, but you are not asking him to learn something. You just pass your knowledge to the computer. And below, there is this subset here, machine learning with neural network and deep learning. And these lessons, mainly all the lessons during this course, will be about supervised learning where you have some data and ground truth, so a matched example. And your algorithm will learn to reproduce or generalize also your data that you have. But there are also two fields like reinforcement learning used a lot in robotics, when you learn to an agent to do some action in an environment, and also unsupervised learning, where you have just random data with no label, and the algorithm has to learn about it. So to master, we can say, the deep learning part, you have to manage with 4 different puzzle parts. The first one is a linear algebra with some matrix operation and derivatives. If you want to know the math behind, you have also to master a bit statistics and probability and some optimization problem, because you have to optimize the parameters of your model to solve the task. And you have to master also some coding skill, especially in Python with PyTorch. But PyTorch is a library that will help you to create your neural network, so that you do not have to code it yourself entirely. So now let's pass a bit to history. So the story begins in the 1940s with these 2 persons, McCullough and Pitts, where they propose an algorithm, the electronic brain, so a formal neuron, a simple algorithm to process some data. But at this stage, the algorithm doesn't learn anything. You set the data, the weights of your model yourself. And later, these 3 people here propose an algorithm to make the parameters of your model learnable, called the perceptron algorithm. And this started a golden age of AI, because it was easy to train and can solve some simple tasks. But after some times, in the 1970s, these 2 persons here, Minsky and Papert, showed or revealed the problem of the perceptron, that is not able to solve a nonlinear separable problem. So it struggles with more complex problem than just here tracing a line to divide the 2 sets. It can't solve this sort of task on the right here. And so this shut down the research for 15 to 20 years. After that, these 3 people here came with another idea called a multi-layer perceptron with another algorithm to learn the weights called backpropagation. It was a bit hard at the beginning, because there were not enough data to train the model, and the computational power were not enough to train those models. So other kind of learnable models came, called SVM, but we will not see here. But starting 2010, the modern AI, as we can say, started with some very deep neural network, thanks to big data sets that we collected, and thanks to some GPU that raised the computational power. So first, a bit of theory. Les diapos, normalement, sont... Alors, il y a ma souris là. Elles sont sur le site. Vous pouvez même les voir normalement en même temps. Là, si vous cliquez... Normalement, si vous cliquez là... slide here. Voilà. Ah, vous n'arrivez pas à accéder au site? Alors.
C'est ça.
Ah, oui, il y a eu. Alors, le site, c'est, au début, il y a, c'est écrit en petit, c'est rufinv. Ah oui, non, c'est écrit là. .github.io /intro. Oui, c'est écrit en petit. Non. Intro. Ah, le I de intro, dans majuscule.
J'étais pas allée jusque-là. Je pense que toi, tu peux.
Voilà. Voilà. Puis il y a aussi, normalement, quand vous cliquez à chaque fois, il y a l'adresse email. Enfin, s'ils les ont mis, oui, voilà, il y a l'adresse. Ah non, pas tout le temps. Vous pourrez demander à ce qu'ils mettent. Mais oui, si jamais vous avez des questions sur un cours spécifique, il peut y avoir l'adresse mail de la personne qui donne le cours si vous voulez poser des questions. Donc, c'est bon, vous avez réussi à voir les slides. Quoi. D'ailleurs, c'est coupé un peu. So we'll begin with the first simple algorithm that I presented at the beginning, the formal neuron introduced by McCullough and Pitts. So it's a very, very simple model that takes as input a vector of size n, so x1 to xn, and output only a scalar value, so just a value in the real field. And this model possesses a set of parameters, W, here W1 to Wn, that are called the weights. So in neural networks, we call the parameter weights. It's something that you have to know. Weights refer to parameters that are learned to solve the task. So the first step to compute this formal neuron is to do a linear transformation. So you have your input x and your set of weights, and you perform a dot product here. So there will be a short recall after. And you add a bias b, and you sum so your dot product and your bias. That's perform a linear transformation. So just recall what is a dot product. You have your two vectors here. You transpose the first one to obtain, so you rotate from vertical to horizontal, and you multiply each element by summing them together. And this is what why we call this a sum, because you sum x1 times W1 plus x2 times W2 plus x3, etc., etc. After that, you have a nonlinear activation function called heaviside function for the formal neuron. So we'll see later what it is. And after this, you have the final output of your model called y hat. And so this neuron was a bit inspired by some biological neuron, we can say. So f is the heaviside function. So this here is a f. It's a heaviside function. It looks like this. So it outputs 1 when the input is greater or equal to 0, and 0 otherwise. So you can see this here. And this allows to have two states for the neuron, activated or unactivated, depending if your input multiplied by your weights is higher than the bias. Here you can see, so this, in this case, your neuron is activated, and otherwise it is inactivated. And there are some other similarities, but that's why that's what they claim at when they produce it with biological neurons. So you have here your input, which are a bit like the axon of the previous neuron, the synapse with your weights. You multiply your weights with your input through what they call the down tree, and then you have the cell body that perform all the multiplication, all the sum, and then it decides if your neuron is activated or not, and give an output through the axon. So this part here. I'm not an expert in biological neuron, but that's the usual comparison. So the formal neuron can solve linear logical problem. So in computer science, you have a simple problem like the and, or, and not. And is like and. If your output is 0 and 0, you output 0. 0, 1, 0, 1, 0, 0, etc. You have to both x1 and x2 has to be equal to 1 to output 1, whereas in OR, at least one of the two have to be 1 to output 1, x1 or x2, and not is just the negative. So if you have 0, you output 1, and if you have 1, you output 0. And this artificial neuron is able to solve such task with those set of weights, for example. And this is why it was studied a lot, because it's so basic in computer science. But for the moment, the weight here were just set by hand. So you don't learn them, just give the model like that, and it solves the task. Then Rosenblatt especially came with this learning algorithm to learn your weights. So here is the algorithm. So you initialize your weights randomly with small values. And to learn them, you have to have a data set with some inputs and ground truth. And so for every sample of your data set, here, you process your input through your model. So this is the heaviside function. It's another notation. It's for the activation function. Then you compute your error. So this is the ground truth that you have in your data set, the Y here. And this is the output of your model. So the error is just ground truth minus prediction. And then you update your weights, W, thanks to this formula here. And you perform this for all the elements of your data set until you have seen the whole data set, until your weights are correct for the task. So we can have a small example. We will try to learn the OR gate. So this one here. So we initialize the weight almost randomly with W1 equal 2, W2 equal 2, and B, the bias equals 0. And your input is 0 for x1 and 0 for x2. For the bias, it's always 1. You perform your sum, and you obtain 0, because 0 times 2 plus 0 times 2 plus 1 times 0 is 0. And then, because you apply the heaviside function, your neuron is activated and outputs 1. After that, you compute the error, so the ground truth minus the prediction. For the OR gate, if both inputs are 0, the ground truth is 0, but your model outputs 1. So you do 0 minus 1, and your error is minus 1. After that, you update your weights. And so here, only the bias is updated, because in the formula here, you can see that it depends on the input, and the input of W1 and W2 are worth 0. And so only the bias change from 0 to minus 1, because you had B at the next step is equal to 0 plus 0, so minus 1 times 1, which is equal to minus 1. And then you pick up the next element in your data set. Here, for example, 1 and 1. So for OR gate 1 and 1 give 1. Again, you pass through your network. Here, the heaviside function outputs 1. You compute the error, and here you don't have any error because you have the good output. And so your weights update will be null. You will keep the same weights, for example, and you repeat that until you have seen the whole data set. This algorithm was a bit the state of the art at the time, but these two people here, Minsk and Papert, show that it was not able to solve this problem here. This was the problem that I showed in the example, the OR problem, but we just have to put a line to separate minus and plus, and the same for the AND gate. But for the XOR, you have to draw two different lines, and it's what we call the nonlinear separable problem. And this kills the research for the next 15 to 20 years. Some people had the idea to use multi-layer perceptron. So this is a bit closer to the modern deep learning, where you stack your different neurons to have a layer, and then stack the layer to have a multi-layer perceptron. So this model is composed of an input layer. So as before, you have an input value, hidden layers here. So here you have only one hidden layer, you can have multiple ones. And an output layer that gives you the output of your model. Here you have two different outputs, but you can have only one neuron to have only a scalar value. So each node here uses a nonlinear activation. And this model is able to solve nonlinear separable problem, like this one here, where you can't only you cannot just draw a line to separate properly the data. And this model can solve those tasks. So this is a more detailed representation of the multi-layer perceptron, but it's very easy, as you can see. So here you have one perceptron, a second one, a third and fourth one, etc. But this is a 2EV notation, and so we pass to this thing, which is much simpler to draw and much more abstract, but less easy to understand, you can see. Yes, so because now you have multiple perceptron and multiple layer, you don't have only a vector of weights, you have a matrix of weights. So you just change your multiplication of the input vector and your vector of weights with the multiplication of a vector as input and a matrix for the weights. Here is a small example. So as before, you just so here x1, x2, and x3 are your input. You multiply your input by your set of parameters for the first layer. So here you have 12 different parameters because you have 12 different arrows normally. And you have one bias for each input layer. And so you obtain at the end those kind of vectors. So this is the computation of this row times this row plus the bias here. And this gives you the linear transformation. After that, you apply the nonlinearity as before, after the linear transformation. And then you do it for the next layer. So this was the set of weights for the first one times the input plus the bias, the nonlinear function, so the EV side, for example. And then this gives you the output of the first hidden layer. And this output is the input of the next layer. Here, you multiply W2 by this result, add the bias, and compute your EV side function or whatever you want. You can add more layer, of course. Here you have only one, but you can add a second one, a third one, add multiple neurons in each layer to increase the capacity of your network. But the problem with this model is it's very hard to train, and it's why it was not very successful at the beginning. But a solution came called the backpropagation algorithm, which is a bit the backbone of the learning in modern deep learning. This was introduced by these three people, and especially Hilton, which is the most famous one nowadays. And so the principle is you just compute the gradient, so the derivative a bit of a cost function so your error term, your error function, with respect to the weights of your network. This is a very simple idea. So just a quick recall, you have an input, and the goal of your network is to map a set of input to a set of output from your training data, so from your data set. So here, an illustration with the inputs, your multi-layer perceptron, and if theta here is just an abstraction of your model. So learning now is an optimization problem. You have a loss, here training loss, that you will try to minimize, minimize. So here you can see during training the loss decrease, and this is trained thanks to some gradient descent. So the first thing is to define the cost function. The most common one is the distance, so the second norm between two values. So you perform the forward pass. You predict your output. So this is a predicted value. In your training data set, you have the true value that your model should have predicted. And you compute your cost function. So your distance or your error term, like in the perceptron. And you will try to minimize this function. Some very common cost function are the mean absolute error. So if you perform the difference between your prediction, the ground truth, and you take only the absolute value. But the most common one is the mean square error, used a lot. Yes.
Est-ce que c'est possible de prendre ce que c'est
Ok, je peux. Donc je peux expliquer en français. Okay. Alors c'est le input layer, c'est pas vraiment, enfin c'est les entrées du modèle. Donc c'est le X1, X2, X3, etc. Hidden layer, c'est la couche, c'est l'empilement de neurones, mais qui va être caché, c'est-à-dire entre deux couches, entre ton input là et le output ici. Et c'est ça donc on appelle hidden, caché. Et output layer, c'est la couche qui va donner le résultat attendu, qui va la dernière couche en fait, avant la sortie du modèle. C'est juste des noms pour dire pour simplifier, en fait, pour différencier l'entrée de la sortie de le cœur, on va dire, le cœur du modèle est là-dedans, dans la partie cachée.
Mais dans les modèles d'avant, il n'y a pas de...
Non, là, dans le perceptron, par exemple, c'était juste un seul neurone. Il n'y en avait pas. Donc, au début, ils entraînaient juste un seul neurone. Ensuite, ils ont commencé à les stacker, à en mettre plusieurs. Et donc là, si on enlevait cette partie verte, lui, ce serait output layer. Et ensuite, ils ont commencé à stacker des layers, enfin, à les mettre les uns à la suite des autres, à les empiler, mais horizontalement, pour avoir un modèle qui ressemble plus à ça. Donc, c'est d'abord un neurone, puis ensuite un empilement pour avoir une couche. Et ensuite, les couches, il les crée les unes à la suite des autres pour avoir un multi-layer perception.
Mais ça, en fait, c'est du schématique, ça existe en vrai. Je ne sais pas avoir. Ouais, c'est pas.
Ouais, le neurone, ça matérialise par quoi? C'est des calculs, c'est un set de calculs.
Le neurone, c'est exactement le même neurone que pour le perceptron. Hop, là. C'était ça, là. Là, il y a input layer, donc c'est celui-ci. Les entrées. Ici, il y a le hidden layer. Hop. Là. Et là, il y a le output layer, ici. Et en fait, chaque neurone, que ce soit dans le hidden layer ou le output layer, c'est un perceptron, en quelque sorte. Il a ses poids. Il sonne. Il y a le biais. La fonction, donc Eviside, en pratique, il y en a plein de différentes. Ça sort une valeur qui ensuite est passée au layer, à la couche suivante, et ça se répète tant qu'il y a des couches à calculer.
C'est physique. C'est
des trucs qu'on utilise.
Ah non, c'est purement mathématique. Dans l'ordinateur, il va y avoir vous allez avoir un vecteur et vous allez avoir une matrice à côté. Et juste l'ordinateur va faire tout seul la multiplication des paramètres du modèle, donc de ces poids, weights, là, avec vos entrées. Il va ajouter le poids. Ensuite, il va utiliser sa petite fonction de non-linéarité. Et pour cette couche, il va sortir son vecteur de sortie. Mais c'est l'ordinateur qui le calcule, il n'y a pas d'implémentation matérielle. Tout est fait c'est le programme qui va le faire à votre place. Mais tout ça, c'est, on va dire, la théorie qu'il y a derrière. Jamais vous allez implémenter vous-même votre matrice de poids, faire vous-même la multiplication, la somme, calculer la fonction d'activation. Tout ça, il y a PyTorch, donc le framework en Python qui va le faire pour vous. Vous allez juste dire en quelque sorte, je veux une couche là, je veux une couche avec tant de neurones ici, une couche avec tant de neurones à la suite, et voilà. Et ensuite, il va apprendre avec ça. Vous n'aurez jamais à faire plusieurs neurones, plus le modèle va être puissant, entre guillemets, parce qu'il a plus de paramètres. S'il a plus de paramètres, il va pouvoir, voilà, tout à fait. Il va mieux ajuster, il va avoir plus de liberté pour ajuster en anglais on dit son knowledge, enfin son savoir entre guillemets aux données. Voilà.
C'est tout nouveau.
Donc on va dire les mots importants, c'est les mots en rouge, surtout. Parameters, c'est les poids. W, c'est les poids. Voilà. Oui. La prédiction, c'est la sortie du modèle. Oui, c'est j'ai pas de panier. Oui, en fait, c'est un synonyme. C'est output et prediction, c'est la même chose. Là, c'est output qui est utilisé, prediction. C'est parce que le modèle, il sort quelque chose, un output où il prédit la valeur.
C'est le résultat.
Voilà, c'est le résultat. C'est le résultat du calcul. Et donc, les éléments en rouge, c'est un peu le vocabulaire à connaître, entre guillemets, input layer, hidden layers, output layer, non-linear activation, donc la EV side function, là, la petite marche, par exemple. Non. Ok, on va. Je vais passer certaines parties du coup. Notamment, j'imagine ça, vous l'avez pas vu. Enfin, les dérivés et les gradients. Ok, d'accord. Pas de cours de maths. Ok. Du coup, je vais simplifier. Que de la bio, ok. Ok. De base. Bon, ben, je vais passer rapidement sur cette partie. Puis on va passer plus de temps sur le TP qui, je pense, est un peu plus clair et montre qu'il n'y a pas grand-chose à savoir non plus, qu'il y a le code fait tout pour vous, en fait. So basically, you just optimize the function For example, here, your cost function, you start here and you want to end here because the model have the lower error, the lower possible error. And so you go through different steps thanks to the gradient here. After one step, you end up here, two step, etc., until you converge to the minimal point. So this is just mathematics. We'll pass through it. Okay. So you compute your gradient, so the derivative. I will say gradient. Maybe derivative is easier for you to remember than gradient. No. You just derivate your function. So your network is just like a big function with weights, and you derivate your function with respect to each one of your parameters. So the computer do it for you, but this is what is done to learn the parameter. And this is a new update formula, so which is very close to the previous one. You have your new weights, your old weights. You have a hyperparameter called learning rate that we will see later, and the gradient. So this is the symbol for the gradient of your cost function, C. So cost function, loss function, it's the same thing, basically. It's to measure the error of your model. And at each step, you will perform one small advance in your minimization process. So yeah, you repeat this thing until you converge to an optimal set of weights of parameters that allows your model to solve the task that it should do. So you have, we said two big steps. First, you propagate your data forward, a forward pass, and then you propagate the error this time backward, so starting from your output to your input. This is called the back propagation. So this is the true term to say that you are learning the weight of your model, and this is done by applying what is called a chain rule. Again, math, but I will skip. This is a chain rule if you want to learn about it, but it's not mandatory. So the chain rule, basically, it's just decomposing your big function. Your model is a big function, but it is composed of small function for each weight. Each weight is a sort of a small function. And so you can't do directly the derivative of your small function for one weight. So you apply the chain rule that allow you to compute the gradient, the derivative of your function for one weight, starting from your big function, and then you go deeper and deeper to the smaller part, a weight, and you see what is the impact of this weight on the error. This allows you a bit to see that this derivative, it tells you, okay, this weight is responsible about how much in the error, and then it will be corrected in consequence. You will adapt the weight in consequence. So first you do your forward pass. So propagate your data forward with your input. This is always one for the bias and your output. After that, you compute your error with your cost or loss function. So C for cost or L for loss, it's the same thing. And then you go backward pass, where you pass your error through each layer and each neuron, and so each weight of your network, to correct them with the right amount, thanks to the quantity, thanks to say that simply. with respect to the quantity that of the error that they are responsible of. Yeah, this is I think a good way to say. So this was an example, but too mathematical, I think, so I will skip. So now, more in practice, how do you compute a forward and a backprop path through some what we call stochastic gradient descent? So you compute your gradient descent, your descent through the slope of your curve of the function, and stochastic because it's a bit random. You have your data set, for example, with digit numbers here. One idea could be you pass your 0, do the forward pass, or your model predicts 9. It's the wrong thing, up, backprop, and correct the weights, then pass to the 7, I don't know, here, and forward, or it's predict 1, again an error, and the backprop to update your weights. This is a very bad idea because you will oscillate a lot. Your weights will change for every one of your data in the data set, and so the convergence will be very hard to obtain. So better idea could be to directly pass the entire data set at one time. So now you have a sort of matrix as input. You pass all of your data, it produces a bunch of prediction, and then you compute the mean of the error of all your data and backprop this mean. And here you have a much more stable case where you approximate the error thanks to this mean error of all your errors. So this is a good idea, but not feasible in practice because usually your data set is very huge and you don't have enough memory in your computer to pass all the data set and backprop all the error in one epoch. We will see this word later in one step. So what is done is called a mini batch gradient descent, where you select just a part of your data set. You pass, for example, the first column here, compute the forward pass, predict some values, compute the error, the mean error, and then up to the backprop to correct your weights. And you repeat that with the second row, the third row, etc. And this is a good idea because your computer have enough memory, so enough computing power to perform this thing. And it's a bit less stable than the previous case, but much more stable than just passing one example, one data each time. Here you will have better convergence. So this, just to visualize a bit the minimization process, in this situation, you have one global minimum. This is an ideal case. This represents your cost function, your loss function. And if you start there, for example, you just do your descent up and end up at the minimum point here without any problem. But in deep learning, because you are in a very high space, because you have a lot of weights to optimize, you are more in this kind of thing, which is much harder to train. So you can start, depending on the initialization of your weights, you start at different places, and you will try to reach the minimum, but you can be stuck at what we call a local minima. So this is a global minima, but here, for example, maybe you have a local minimum, and once you are stuck there with the algorithm of backpropagation, at the end, you will not be, or it will be very, very difficult to get up there again to go through the global minima. So you have no guarantee that your model will end up in the global minima, that it will solve the task optimally. It will solve the task, but maybe in another manner that is not optimal, but it will solve it. So this is an example where you have two minima, and depending on the initialization, you can end up in different setup with here a local minima and here a global minima. And so what is done, it's you initialize your weights in a lot of different manner, and you see the average performance, for example, of your model. And this is just a short illustration to summarize the big principle of deep neural network. So there was this forward pass with input, hidden, and output layer. So here, two hidden layers. So you compute your forward pass to make the prediction. Up here, it's output y hat or y prime. You compute the loss, and then you backprop the loss here up through the input layer. And this will update your weights, your parameter of the model. For the coding skills, so this is just an example, but we will see this more in detail during the practical work, but you have not so much to learn. Python, and especially PyTorch here, will do the job for you. For example, here, optimizer point step is basically the backward. So very simple to implement. And forward is the forward pass, for example, so very literal. And here some useful resources if you are interested to learn a bit more about it. So now we'll pass to a more practical part. It's not the practical work, but a more less theoretical, we can say. So to train your neural network, you first need some data with a label. So here is your input, here's your label. You have to define a task, so what your model should do. You have to choose an architecture for your model and choose the right loss function. And then you can begin the optimization process. So do the prediction, backpropagation, etc., etc. So this is an example where you're with the MNIST dataset, so handwritten digit. The task is to classify the digits. So the 0 images should be classified as 0, 1 as 1, etc. The architecture here is a bit special, the convolutional architecture that I will just introduce later, but you will have another lesson about that, how to build this kind of architecture that are made for images. And you choose your loss function. Here, it's called the cross-entropy loss, so you don't have to know the mathematical details, but we will see some loss that are useful depending on your use case. And then performing the prediction, backpropagation, etc. So multi-layer perceptron, also called MLP, this is a standard solution. This is the most simple one, but used a lot for data with simple structure. So when you have a vector as input, and here we can you have an example where you can see you can create your own network very simply. So, for example, if we have only one neuron, as before, you start the training, and it is able to separate very nicely your blue and orange points. But if you have more complex data, like this one, this is literally the perceptron, except for this one. This is not the same activation function, but and you can see that it tried to draw a line, but this line is not optimal at all because the model is not powerful enough to solve this kind of classification. So you can add some neurons up here, here, and here. For example, and here it will be again, yes, it's because also you can add some over multiple data, and here it starts to be a bit more accurate thanks to an augmentation of the size of the network and to data augmentation. So when you modify a bit your data to input more different things in your neuron, in your model. Here, for example, it is able to separate nicely the 4 different squares. So you can play a bit on this website. Oh. Okay. Ah, voilà. Mince. Oh, non, alors, j'ai fermé la présentation. Hop. Hop. Okay, so this was the website to play with the different layers, different architecture. And so now is the question how to choose the right architecture. So you have some vegetables and you want to cut them. So what you will use a wood knife, a real knife, or a chainsaw. You have different possibilities, and if you have a too powerful model, you can have some trouble. The same with too simplest one. You have to choose the right one. Here's a knife. So here are some examples. When your model is too complex, so if you choose a chainsaw to cut vegetables, you will have some overfitting, what we call overfitting. So this case here, you see that for your training data, your model predicts very well your training data. You can say, oh, perfect, but there is after a lack of generability, because if you have a new data that is here, for example, you will struggle, or here, you will struggle to predict the right value, contrary to this model here, where you see that it has some error, but globally, it understands the global behavior of your data. Here, this sort of curve here. But if you have a too small model, you will end up in an underfitting setting, like this one, or like the perceptron one with XOR problem or nonlinear separable problem. Your model just draw a line to predict the value, and this is not enough. You will have too much error. But at least you will be very efficient in time because your model is very small. So if you are limited in computational powers, you may underfit. Whereas if the model is too complex, also because it has a lot of weights, it will take a lot of time and memory to train, and this is not efficient at all. So how to choose the architecture? Because for the moment we only saw MLP, multi-layer perceptron with a simple neuron, etc. This is great to deal with vectors of values. It's done for that, but you have multiple different inputs. You want maybe to pass some text to your model, some time sequence, so sounds, for example, images or graphs. And MLPs are not created to deal with all these different things. For images, you will mostly use, the most common thing is a convolutional neural network, CNN. So we'll not enter into details. You will have a lesson for that. But it takes inspiration from a different part of the brain. So V1, V2, V4, where you stack some layers of convolution. And at the beginning, it looks more at the edges and the lines. After the shapes, then the global object, and at the end, for example, faces, etc. So enter more and more into details as you go in the deeper in the convolutional model. And so this is very good for images because it can capture some local information For example, here the eyes is close to the mustache, whereas the multi-layer perceptron can't do that because you have to linearize your image. So you put this vector here, and no, you put this vector here, for example, below this one, and do this also for this one. You put it under the second one, etc. And at the end, you have just a vector with no spatial information at all in it. So this is not optimal for big images, and it's why we use convolutional neural networks. For text, something that was used a bit less now is recurrent neural network, because text is like a sequence, and the MLPs are not created to deal with such a sequence. So basically, RNN is a different MLP concatenated together, we can say, that has a memory hidden here. So hidden state, the blue things here, it's just the memory. You input I to your recurrent neural network cell. It will process the thing and remember that first it saw I, then am, process the thing, remember that first it saw I, and then am, etc. And this hidden state act like a memory, maybe to related students with I, for example. So that the model can understand that student and I are the same thing in the sentence. I think you will have a lesson also for this one, if you want one day to deal with sentences like GPT, for example, but it's not a RNN at all behind GPT. And then you have to choose a loss. So these are some examples of loss to use. Because the most common things is you have two main problems in deep learning that are classification. So you want to classify your data, here blue versus red versus green, or to do a regression to predict a line that match as much as possible your data. And so, because you change your task, you will have to adapt your loss. Your loss is linked to the task you want to do. And for this, you have a bunch of losses that exist. And here are some examples, cross-entropy or hinge loss for classification. So I will not enter into detail, just if you want one day use it there in this slide. And mean square error or mean absolute error for regression. So these are very common losses to deal with these two problems. But there are others you can see on the internet. There are a lot of resources on the internet to find new losses for your problem, etc. Then for the training and evaluation process. So at the beginning, you have a big data set, but you are only using it for training. Until one point, you want to evaluate also your model. So you divide your data set into two separate things, a training part and a test part. With the training part, you optimize your model. With the testing/evaluation, for the moment, you test if your model generalized to unseen data. And so for this, you use your metrics, etc. And this is a representation of the process. You predict, you do the backpropagation, the gradient descent to update your weights up again and again. And once you have seen the whole training set, you pass to the evaluation set. But this time you just compute prediction. You just want to see if your model performs good on other data without doing any backpropagation and gradient descent. The goal is not to learn, it's just to see the performance of your model. So the gradient descent, stochastic gradient descent is computed during each step. So this is a step. This thing here is a step on your training set. And we call an epoch when you do an entire pass on your training data set. So when you have seen all your training data set, we said that your model did an epoch. It's a vocabulary. And, so this, for example, is a step. This small arrow, you perform one step. then another one, etc. And then there is a question, when does the model stop learning? The first perfect thing is when the cost function reaches the minimum, when the model has converged. So this case here, perfect, your weights are stable, you are in a minima. So you stop the training and just apply your model after that. But there are some cases when you have too big model, for example, or not enough data, your model can overfit on the training set. So here it's not the loss, it's the accuracy. It tells you if your model is good or not. So higher is better. And so you can see the training, the performances on the training set keep growing. So it's better and better. But on the validation set, so unseen data, it's learned at the beginning, it generalized, but at the end, poof, the performances decrease. And this is why also we use a validation set to see if your model is doing overfitting. And then you stop the training, for example, at this point here, where the validation performance are the better. The perfect thing is to divide your data set into 3 different things. So the training part, the validation part, and the test part. You perform your epochs, your steps, and your epochs on the training set. At the end of each epoch, you pass to the validation data set to see if your model is doing overfitting or not. And then passing again to a training set, etc. And until you have done the right number of epochs, so this is usually a hyperparameter, but you said to your model, okay, you will be training for, I don't know, 100 epochs. At the end of the 100 epochs, your model will pass to the testing set to give you a final values on real unseen data, because sometimes you can optimize your model to perform good on epoch on validation set, but not on the testing part. So this is just another step to be sure that your model is generalizable. Also, there was this parameter with your gradient descent called the learning rate. So this parameter is really, really important because if you have under a too small learning rate, so the learning rate will scale your gradient, the amount of correction you will give to your weights. You will perform a lot of steps. You will compute a lot of steps to reach your minima. Whereas if your learning rate is perfect, you will do very few steps to pass from the beginning to the optimal point. Having a lower, too small learning rate is not a fatality. It's just that it will take more time for your model to converge. But having a too big learning rate, it can be an issue because you see that you try to reach the minima in this case, but you are going from one side to the other. And so it can be very hard to reach the minima. But in the worst case, you can also diverge because you are applying too big step. You said to your model, okay, so the gradient here is going in this direction, but because you scale your gradient too much up, you are passing through the minima and going on the other side, and then again up here and here, and your model will diverge. So you have to set a good amount for your learning rate, not too big is the more important thing. Too small is not that important compared to a too big one. Also optimizers. So to perform this gradient descent, you will not do it by hand yourself. You have some implemented optimizers that are complex technique in math to optimize your gradient. The most famous one is the Adam optimizer, which is an extension of stochastic gradient descent. And it's the most used in deep learning nowadays after stochastic gradient descent. Here you have some examples of optimization with different algorithms. And you can see that some of them get stuck in this minima here, whereas others are able to find a new way. So this is why we use a more and more complex optimizer to find a good solution. One of the last thing is regularization, because you have a lot of weights. I don't know if you remember, but we were in this case here with a very sharp cost function, and we want to end up in a case more like closer to this one here. For this, we use what we call regularization to simplify the optimization process. And so there are different things that you can try to add to your optimizer, like dropout, early stopping. So early stopping is for the overfitting, for example, stop the training as soon as the evaluation loss start increasing. It was what I presented before. Weight penalties so that the weights don't grow too much. And also you can perform some data augmentation. This is a very common. You are augmenting your training set. So for example, with an images, you change a bit the color, you're doing some rotation, some flipping, etc. And keeping the same label, but to tell to your network, okay, this image is flipped from with 2 degrees, but it's the same image. So that it can be robust to some changes. And these are some techniques used to make the learning easier. So passing from this to this. So with the learning rate, the regularization process, the optimizer to choose, etc. All of these things I call hyperparameters. Also, the number of, if you are using a MLP, for example, the number of layers, the number of neurons per layer, etc. All of these are called hyperparameters because you are not learning them. You are just setting them by hand and then perform the training. And so you have to do some choices of architecture, losses, optimization process, etc. And to find the best set of hyperparameters, so the best architecture, the best loss, cost function, or the best optimization process, we do it often manually. So we test one thing, see the result, okay, it goes like this. I will change the number of layers because my model is not powerful enough, or my model is too powerful, so I will decrease the number of layers, etc. But there are some techniques called grid search and random search that are implemented, I think, in PyTorch, so that you tell to your algorithm, okay, you will perform some training with this set of hyperparameters, for example, 2 hidden layers, 3 hidden layers, 4 hidden layers, and two neurons per layer, 3 and 4, etc. And you will see the results, the performance of your model with respect to each one of these hyperparameters. And at the end, you select the best one, of course. So before passing to the Python code, here are some examples of nowadays deep learning algorithms. With OpenAI, you have GPT and DALL-E 4, AlphaFold 2 in more biology or chemistry thing, Midjourney, which is a bit the equivalent of DALL-E 2, no DALL-E 3 again, to generate some images, but you have also a lot of application in robotic with Palmi. So where you tell to the robot, bring me the right chips from the drawer, and the robot will go by itself, so it was not programmed for that. It has find the drawer, open it, and take the chips. And even when he thought he had the chips, here the human will put it again, and the robot will say, I didn't pick it in the right way, so again and again. And these are some, for example, last result in robotics with AI boosted robots that have learned to live and to perform some given task in the environment. The end. So that's where we are nowadays. And now practical work, but maybe we can do a short pause if you want, because it was a lot of thing to digest. Peut faire une pause de 5 minutes au moins. Et puis après, de toute façon, je passerai avec vous, je pense, sur le TP. On fera ensemble ces mots-clés. Donc, vers entre 20 et 25, je reprendrai. Yeah. Mais après, les évaluations ne seront pas, ce sera poursuivre un peu les TP. Il n'y a pas besoin de connaître tous les détails de ce que je viens de présenter. Là, il n'y aura pas besoin de PyCharm normalement. C'est disponible sur Google Colab. Donc, parce que je ne sais pas si en STP on utilise les GPU. Mais de toute façon, tous les TP sont sur Google Colab parce qu'il faut une carte graphique pour faire les calculs, ce que les PC portables n'ont pas forcément. Si vous avez des questions, n'hésitez pas soit à les poser, je réponds en français, ou sinon envoyer un mail. Et enfin, je pense que même si pendant le TP, il y a des choses qu'on utilise et que vous avez au final pas compris, je peux répondre en français, pas de souci.
Ouais. C'est longtemps qu'on n'avait pas même question.
C'est cool.
Non, je sais pas. On dit ça, rien, mais je fais tout le temps comme ça. Donc, ça va, c'est pas.
L'EPP, vous voulez le faire en anglais ou en français? Ah, vous avez. Ah, ok. Bon, ben, on va le faire en anglais du coup. Non, mais vu que c'est enregistré, j'imagine que pour qu'elle comprenne. Mais si jamais vous avez des questions en français, vous pouvez répondre en français, il n'y a pas de souci.
Tous les mots sont enregistrés.
Oui. Enfin, de ce que j'ai compris, ouais.
Oui, il
n'y a pas de souci. Hein. Il y a pas d'appel, je crois. Donc, c'est juste les projets à la fin qui sont notés. So, let's pass to some practical work. So, Python code. You have a link normally to go to the Google Colab, so notebook, so that you don't run the code on your own computer, but on Google servers. It's on the website normally. Notebook here, voilà. But otherwise, I will project the code so that you can follow with me. But maybe it's more useful if you can run the code at the same time to see if it works for you, and more practicing a bit more to learn a bit more how to code. So these are just a first line that are not that important, just to install some packages, NumPy, Panda, Matplotlib, to manipulate data. The ones that are interesting are Torch Vision and especially Torch. Torch will create the model for you, compute the backward for you, update the weights for you, etc. So very useful to create and train your model. Also deal with all the data. It will create the data set and divide it into train, test, validation, etc. So it's very useful. The first thing to do is to import the libraries. So NumPy, Pandas, NumPy to deal with some matrices, Pandas with some data frame, so like Excel sheet a bit. Torch and Torch, these are just some also import for to create your network. And then it's for neural network. Matplotlib is just to plot some nice results. So first, let's begin with a recall about the perceptron. So here, for the first one, it's just an illustration of the perceptron. We will not use PyTorch here. It's just to illustrate how it will work. I don't know if you see very well on the screen, but otherwise maybe you have your computers. So the first thing is to define some input data, X. It's a triplet with your input for the X1, X2, and your bias. These are the ground truth elements. So the ground truth for for the OR gate, the AND gate, and the XOR gate. So for example, here you have an input with 0, 0, and no, this is not a good one. This one is better, 0, 1, and 1. So these two, the first two are more important. If you have 0 and 1, for the OR gate, the output will be 1 because you have 0 or 1. One of the two is 1, so you output 1. But for the AND gate, your ground truth is 0 because you have both input have to be equal to 1 to output 1. And for XOR, it's more complicated, but the ground truth is 1. It's just to see that your perceptron can't learn good ways to solve XOR. Now, no. So just create this bunch of vectors. So X point shape will give you the shape, basically, of your vector X. 4 by 3 because each element here contains 3 values inside, and 4 because you have 4 different vectors. First one, second one, third one, and fourth one. And for the ground truth variable, here is y XOR, you have only 1, 2, 3, 4 values, so a shape of 4. XOR. Ah, c'est une porte logique en informatique, un peu comme OU et, mais un peu plus complexe, qui... parce que j'ai pas une illustration, c'est peut-être... Ah ouais, mais pas ça. Voilà. Où ça... Il y a à chaque fois 2 inputs, et ça fait en fait en quelque sorte ce calcul 0, 0, ça output 0. Là, quand il faut qu'il y ait un seul des deux qui est un 1 pour que ça en renvoie 1, mais si les deux valent 1, alors ça renvoie 0.
C'est des scénarios, non?
Oui, voilà, c'est un peu des scénarios. C'est basique. Oula. Ah, qu'est-ce que c'est que ça? Ah, c'est le site. C'est différents scénarios, des portes logiques utilisées en informatique. Donc, c'est juste que celle-là est plus complexe, beaucoup plus complexe que juste un et ou un ou. So then this first line y equals y or is just to choose that your ground truth you want to learn on. Here we will want to learn the OR gate. Here you just initialize your weights randomly with NumPy. So random point rand 3 will gives you a vector of 3 elements that are randomly initialized, and you initialize also some parameters. This one is important since the maximal number of steps to perform, because you will see that for y XOR, if you want to learn the XOR gate, your network, your algorithm will just learn infinitely because it can't converge to a good value. And so this while is basically while you haven't reached basically the maximum number of steps, this is the most important part, you perform your training. So you choose your, you perform your dot product between your weights that are initialized randomly and your input X, and apply the EV side function. Then you compute your error, Y, which is your ground truth, here the OR gate, and your prediction, Y hat, and you update your weight. And these are just some bunch of computation to be sure that the model will stop at a point for the XOR case. And if you learn it normally, it has taken 13 steps to converge. But if we choose Y XOR, here we will see that 1,000 steps, we reach the maximum number of steps, and if we choose a large number, it will run and never converge. So the perceptron is not able to learn the XOR gate. As we can see here, it just indefinitely sees the data and don't learn through it. Yeah, basically what I said. That's the green part. So green part are comments, but c'est aussi pour vous, pour tout le monde a le code. Ouais. So for this part, this function is just used to classify some. You run your algorithm with this time torch, and not NumPy. So Torch is the framework used for the more classical framework used for deep learning stuff. And here you see, so you have data here, the 1, 0, 0, 0, 1, 0 here, and another one here. And this is the XOR case. And you can see that to classify correctly, it should have drawn a line here and a line here. But because it's a perceptron, it just separates here in this case. So countable to here, it's a red dot, but it is classified as a green dot. So the perceptron miss is not powerful enough to solve this problem. It was just an illustration for the perceptron because here we don't use a torch, and so we have to perform all the things manually. But this is not interesting to do. Aside for the example of the perceptron, here we will pass to a more real case, we can say, using PyTorch. So we will try to tell if a cookie is good or not, basically. So in your data set, you have some data with the number of chocolate chips per centimeter square and the size of the cookie here in radius. And there will be a label according for each one of these cookies telling you, okay, this cookie, for example, is a good cookie. This one is a bad cookie, etc. This is in your data set as a ground truth. And so your model will learn from it. So here, this part is hidden because it's not very important. It's just to create the data set. So you just have to run it one time, but I will not explain what it does because it's not the point here. Hop. No. Okay. And here you can see just the distribution of your data, the radius of your cookie, the number of chips per chocolate chips per centimeter square, and if the cookie is good or not. Up. Here are some example, and here's the repartition of your data. So this is done with Matplotlib. Just if you want to visualize your data, Matplotlib is a good thing to use. And you can see, so in your training data set, here it's the radius of your cookie, and here's the amount of chips you have. So in the middle, it's the good cookies that are represented here, and here on the border, it's the bad cookie. And we can see that for the validation data set, it's quite similar. The good cookie in the middle and the bad in the border, and same for the test data, but a bit more noisy. Here, for example, you have some good cookies, whereas in, for example, training data set, this part is more labeled as the bad cookies. So just to show that you have some shift between your training and testing data sometimes. I will just hide this part and get cookie data. No. Non. Ce qui reste. Hop. Alors, so the first thing to do to give your model your data set, basically, is to create this data set with Torch. So you just, do you know what is a class in Python? No, it's like a big object which have some properties and function. So for example, here there is a class cookie. Inside this class have some parameters like the df is the Excel sheet of all the data contained in it. And we divide this Excel sheet into first the data, so the radius of the cookie and the number of chips, and the labels, So the values if the cookie is good or not. And these are the two main things in our class. And after that, there are some function in this big object. Len is to capture the length of your data set, so how many data you have, and get item is just to return the data you want to have. So for example, if you want to have the first data, you will give here index 0 because in Python it begins with 0, 1, 2, 3, etc. And it will return you the first element of the list. So here you just create your data set, and then you have to define your model. So here we will use a linear layer. So here you just have one linear layer. So you don't have to define a big model, just MN for a neural network, which is a part of Torch, with linear for linear layer, and then you give some parameters. Here, for example, the input side will be 50, and it will output one value. And you can see I printed the weights. Here are the weights of your layer that are initialized automatically by PyTorch. And so requires grad tell you that your model will learn thanks to the gradient. And you have also, so here it's your weight size, and here it's your bias. You have one bias because only one output. So to create a linear layer, you just pass nm.linear. Very, very simple. And do the same here. And you see, it was to illustrate that when you do the same thing, your weights are initialized in a different way. Here you see a first initialization, and here a second one. And if I rerun the code, another one. Each time you initialize your weights, PyTorch will automatically change the initialization to have new results. And then a new initialization will lead to another optimization process. Maybe with this initialization, you will end up in a global minima, whereas with another one in a local minima, just to have a mean average of the performance of your model. So now that we know how to define a linear layer, we will create a bigger model called multi-layer perceptron, MLP. And again, the goal is to create a class, an object, which is, it's complicated, but to create a big model in PyTorch, we have to add this NN point module to tell that your model is a PyTorch model. This is just to say, okay, my MLP is a PyTorch model that will learn thanks to PyTorch things, etc. So these are some initialization. And here you define the first linear layer. So you have only two inputs, the size of your cookie and the number of chips. And you choose how many outputs you will have for your model. So for example, here you have 10 hidden, not layers, but 10 hidden neurons in your layer. You pass from 2 to 10, and then you can create another linear layer from 10 to the number of classes that you have. Here it will be 2. And here you choose the activation function. So during the presentation, and only talk about the EV side function, this sort of step. Here we will use tan h, tangent hyperbolique. Don't enter into details, but it's one common to use tan h or really other things than EV side function. But you can just copy paste this for other things, Tanash, Relu. And then you define, so the important thing, the forward pass. So first it's a Python function with self is just to tell that this function is part of your MLP model. And input will be your input. So basically your X. So first you pass your input through the first layer, FC1, here, because we put this linear layer into a variable called FC1, and then pass this to the activation function tan hash, and then pass it again to the second layer with no activation because we want to classify, so it's a detail, but at the end we don't put any activation to have a good classification. And so your model will have one layer with an input layer, one hidden layer with an input layer of size 2, 10 neurons inside your hidden layer, and 2 neurons, sorry for the number of classes, in your output layer. So this scheme here you will have 2 values, 2 dots, here 10, and here 2. Up. So these are just some figure to explain. So here it's to start the training. So you pass, of course, the path of your data, cookies, cookies train, cookies val, and cookies test for each of your data sets. So the training data set, the validation data set, and the test data set. Here it's just the number of classes, and here starting the hyperparameters. So you define the max number of epochs you want to train your model on, and the batch size, which is how many data you will see per step, and the learning rate, so the amount of the scale you will give to your gradient to update the weights. So
Je veux bien compter la différence entre une max epoch et une batch size.
Max epoch, c'est le nombre de fois qu'il va voir le dataset d'entraînement.
Okay.
Donc, il va le voir ici 1800 fois. Et batch size, c'est le nombre de données qu'il va voir à chaque step. Donc, à chaque fois qu'il va faire une forward pass et ensuite qu'on va faire l'erreur et tout ça, il va voir 32 données. Ça va être 32 par 32. C'est ce qui avait été montré au début, c'est utiliser une donnée à chaque fois, c'est pas tenable, voilà. Tout, c'est pas possible. Et là, on utilise 32 parce que c'est une valeur qui a été fixée comme ça, mais qui fonctionne.
Et c'est à chaque fois, il va y avoir 1800 fois le même batch.
Le même batch, ouais. C'est juste pour qu'il...
Si vous voyez 32 petits à chaque fois, il doit terminer 1800 fois à niveau
il voit 32 cookies à chaque step.
Okay.
Donc, à chaque fois qu'il prédit des valeurs, il voit 32 cookies.
Okay.
Ensuite, il corrige la valeur pour ces 32 cookies. Il revoit 32 cookies, les 32 suivants du dataset, etc. Et quand il a vu tous les cookies du dataset, là, il a fait une époque. Donc, il a fait qu'une époque sur 1800 et ensuite, il va recommencer à revoir les 32 cookies à chaque fois et ça 1800 fois.
Et le batch size, c'est déterminé selon la puissance de l'ordinateur?
Oui, en fait, ce qui est fait souvent, c'est le plus gros batch size possible jusqu'à ce que l'ordinateur dise « je peux pas ». Voilà.
Et c'est quoi le learning rate?
Le learning rate, c'est, je ne sais pas s'il y a encore c'est à quel point on étend ou on rétracte la flèche. Si on met un learning rate plus petit que 0, la flèche va être plus petite, on la scale un peu moins, on va faire des plus petits pas à chaque fois. Par contre, si on met plus grand que 1, bon, ça arrive jamais. En général, le learning rate, c'est vraiment tout petit, c'est 0,0003 par exemple. Mais si on scale le learning rate plus grand que 1, ben, on va faire des plus grandes steps. On va agrandir la flèche. Et c'est là qu'on risque de, par exemple, d'aller de l'autre côté directement sans atteindre le minimum. Donc ça, tout ça, c'est ça, c'est le style d'hyperparamètres qu'on fixe à la main, avec aussi l'architecture. Là, c'est pas très flexible comme code, mais ça, c'est aussi un hyperparamètre. Le nombre de neurones dans la couche cachée et le nombre de couches de layers. Et aussi cette fonction-là, tan h. Ça, c'est des choix à faire. So after that, now that we have the path of our different data set, we just create our cookies data set. So the training cookies, the validation cookies, and the test cookies. And PyTorch has something called data loader to load the data inside your model. So that at each step, you will see 32 data. This allows you to perform that automatically. Let PyTorch do it for you. But it's important to do it. And especially when you run on GPUs, it will automatically pass, because your data are not directly on your graphic cards. It passes from your CPU, your Intel things, to the graphic cards for you, so that you don't have to run the code to tell him, okay, no, you pass data to this part of the computer, etc. PyTorch do it for you. And here you create your model with the number of classes for the output layer. So we have 2 classes. And your loss. So here, because we want to do classification, bad or good cookie, we use the cross-entropy loss. And as I said before, you don't rewrite your loss mathematically. You just type, you have a lot of documentation if you type PyTorch. Here up on the website, and you will have some documentation, etc. Get started, docs, up. And you will have a lot of things that you can see to choose the right loss. PyTorch have a lot of things already implemented. So here it's just to create your data set, your data loader, your model, and your training loss. Now you have your training loss, your model, your data set. The missing part is the optimizer, because you have to do this backpropagation thing. And this is done thanks to Optim in PyTorch. So this SGD for stochastic gradient descent. So here we don't use Adam as I said before, the mostly common one, but SGD because it's a very simple use case. And you pass some parameters to it. For example, basically the learning rate is one of the parameters to pass to your optimizer. So this part is just to create the optimization part. And now, here. Yeah, this is a bit train model here. And now we will train the model. Passing some, no, here I created a dummy model. This is not, no, this is not here. Voilà. So, for here you do a for loop. This for loop tells you how many times you will repeat this training. So basically, how many epochs you will do based on these hyperparameters. Max epoch, here you can see that max epoch is equal to 1,800. And it will repeat the code inside this here, this thing, 1,800 times. So you set the first thing to do is to tell to PyTorch, okay, now my model is in a training mode, because after training, you have different mode for your model. First, you train it. So you tell to PyTorch, okay, I train my model. And after that, you tell PyTorch, okay, now that my model is trained, I just want to use it without optimizing the weight anymore. So you change the mode of your model from train to eval, for example. So here you do the loop for each epoch, set your model to training mode, create some dummy variables that are not important. And here you have your train loader, so the data loader that was created before here, to pass the data to your model in a good format. And you iterate on the data in your training database dataset. So you have, for each data, you have the input that you will give to your model, so the number of chips, chocolate chips, and the number of the size of your cookie, and the label if the cookie is good or not. This is not important. You initialize the optimizer basically, and then here is the important part. You predict the output of your model. So here it's your model variable, your MLP. You give an input. So here 32 cookies, and it will predict you the result, so the class of the cookie. Here you compute the loss between your prediction of your model and the labels that are in your training data set. This is done automatically by PyTorch also. And then the backward is done also automatically. Lost point backward will optimize, not really. It will compute the gradient basically. And this line of code will optimize all the weights for you. You do an optimization step. So this part of code is the most important one to retain. Main steps here. Then this is just some log thing. And if you run the code, up, here you can see that it learns. Up. The accuracy is stable. So here, basically, the model already converged because the loss don't move so much, and the accuracy is pretty stable. Maybe 1,800 was a bit too much. But once it finished, it draws some plot of the history of the learning. Okay. Here, and after that we evaluate again. So test, here we pass some test data and just want to evaluate the performance of our model. So we pass the input, etc. We iterate over the data set up to see if the model is correct. So on the training set, we can see that the model have an accuracy of 63%, on the validation of 68%. So it's a bit better, but in the same quantity. But there is a drop in the test set of 59%. This is maybe due to the fact that we have seen it before. There is a bit more noise in the testing data here, for example, and the model don't generalize to these cases because it is considered as outliers, for example. It's just noise in the data. But here you can see you can see the performance of your model. And with this code the loss of your model during the training and the validation. Up, you can see that the loss reaches the minimum value after 500 epochs, for example. And so 1,800 epochs was way too much epochs. You could have stopped the training at 500 epochs. And the accuracy was pretty stable. Here are just some illustration to show you that indeed, here are where the good cookies are classified by the model and the bad cookies. And these good cookies here, for example, are classified as bad cookies. So to illustrate why the test performance are worse than the training one, but this is often the case because your data are not always the same. There is always a bit of change. So it's why it's important to not overfit and to be the most generalizable as possible. I think the time is running. So just this is just a part with classifying images with NIST. So basically, here are some code to import the data, etc. And here you create your data set. It's a pre-implemented data set, so you don't have to create a class, etc. It's imported from a website. Here you have to you create your network with the number of layer and number of hidden layers, number of neurons per layer you want, etc. And you do the forward pass. Here there is a warning because you have images, so matrices, and your MLP can only deal with vectors. So you vectorize your image by just you have your image with a grid like this. And to linearize, we do 0, 1, 2, 3, 4, 5, etc. We pass from a matrix to a vector to give it to the model. So with this, you lose all the spatial information and you take just a vector. From NIST, you will see that still MLP can have very good performances because it's a very simple case. The 0 are always pretty much the same, the 1, 2 extra. But convolutional neural network will have better results with this type of data. So this has to be done before classifying images to linearize, to pass from a matrix to a vector. And after that, it just show you pretty much that it's exactly the same code. You create your network, your cross-entropy loss for the classification, your SGD, same code, but the only change is the hyperparameter that you choose and the data that you have. And here are just some exercise for you, because here you can see that there is nothing in this part of code. So basically, you can almost copy-paste the previous code in this different cells. Here it's called a cells for a notebook. And here recopy the main steps also, just so that you manipulate a bit the code to understand better or to learn better how to code for future. So here the code will not run, but you can do it at home if you want. Send me if you have any question about it. Why is it? If your code isn't working and you have some problem, you can send me emails and I will tell you what to change. Or if you don't understand something in this part of code, you can also send me emails so that I can help you. And I just wanted to show you, because you will have to do a sort of project. So to continue a practical work of one of the lessons, And so here are some insights of what to do after the evaluation part. So you can here are some ideas what to do to go further for the evaluation, to change the byte size, the weight decay, do a small study, for example, what is the impact of the batch size on the performances, what is the impact of the weight decay. So weight decay is just a regularization process. What is the impact of a learning rate? Change the activation function to ReLU, because it's tangent hyperbolic, and ReLU is the most used one nowadays. So to see if the performance increase, add some regularization, change the optimizer to Adam. I'll put you some link to just change from SGD to Adam. Add batch norm layers. I also put you a link. Basically, it's like a linear layer. It's the same, but with other parameters to enter. And all the documentation is on the internet. And you can also try to implement some convolution, but of course, not directly after this lesson, because you haven't seen it. You have an example here. No, not even here. Here it's only linear. Here it's an example of a batch norm 1D. And here an example of a conv 2D with ReLU. So you have some other example below. But next time with Benjamin, I think you will see how to implement some convolution on images. And so maybe you will be able to try convolutional neural network on this data set list here. So these are just some insights for later. And yeah, this is the end of the lesson.
So for the evaluation, you have to do all those things?
No. You choose, you are not even, you don't even have to do one of those things particularly. It's just some insight ideas for you to what to do, what idea you can have to do a small project about this particular lesson. Voilà. You choose, for example, 3 or 4 things, different things that you implement, and then do a small study, for example, why you choose this, what is the impact of your choice. This might be important for this part, because here the most important thing to know is that you have to some choices to make: architecture, losses, optimizer, etc. And what are the impact of those choices on the performance of your model? So yeah, this is the end. So if you have any question, you can ask me now or send me emails, even about this. So the lesson or the practical work, because the practical work was very short. We didn't have a lot of time. So don't hesitate to ask a question, of course. Du coup, je vais quitter le Zoom. Stop share. Voilà. C'est ça.
À chaque fois, dans chaque practical work, ça sera